So funny you should say that, because we have a thing that I'm going to call the fundamental theorem of PSRs, but we could just call it the PSR theorem, that says specifically any n-state POM-DP can be represented by a predictive state representation,
or PSR,
with no more than n tests, each of which is no longer than n steps long.
Oh, so that's good. But also, you just introduced something, the number of steps. I guess I didn't think about that before, since both of those tests were sort of...
They were very short, right, yeah. But, and it's not hard to come up with an example like that, right? And I'm writing it as a POM-DP because I am a, limited beast. And it's hard for me to think about PSRs. So what might a test be that you'd need to represent, a POM-DP written like this? So we've got, white state, black state, black state. So one-step test would be things like, if I go, well, there's only that one action, and I see white, what's the probability of that? That's not enough information to know where we are, right?
Right.
And in fact, seeing black is also not enough in this case. We actually have to think about what happens in 2 steps from now.
Right. So yeah. So you could say if your test is 2 steps away, then I could, for example, figure out if I see a white and then I see a black, then I know I must have been in the bottom state.
Right.
If I see black after making one move, then I had to be in one of the 2 middle states.
Right.
And I guess if I took 2 steps and I saw white twice, then I know I had to be in the top state, for example.
So are you saying that you think we need another test to make this go?
Well, I don't know. I'm just occurs to me that I can figure out that I'm in the top state if I see 2 white ones. That's all. I'm just pointing that out.
Well, wouldn't it be enough to just know, okay, if I go up, will I see white and then go up and see black? If the probability of that is 0, and going up and seeing black, the probability of that is 0.
Oh, so if going up I see black, the probability is 0, then I have to be in either the top state or the bottom state. And if it's also the case, if I will not be able to see white and then black, then that tells me which state I must be in.
Yeah, that was the thought.
Right. Yeah. Sure.
But these longer tests are really important here. Just having the single step doesn't give you enough information, doesn't give you enough constraint.
With those 2 tests, can I alone figure out everything? Can I completely disambiguate?
So I think it's like the other example that we looked at, which is if we know that we're in one of these states, top, second, third, fourth, then I think these 2 tests are enough to tell us which of those 4 things we're in. But in general, a belief state might be something like, well, 0.6 of the top one and 0.2 of the second one and 0.1 and point something else. So in that case, we've got a 4-dimensional vector, actually a 3-dimensional vector because it has to add up to 1, that we're trying to specify by way of 2 numbers, and we get that same kind of indeterminacy that you worked us through in the other example.
I see. Okay, so this kind of makes me want to ask a question.
Okay.
Why does this help? Why should I bother going to PSR other than the mathematical niceties?
There are some examples where it helps, and part of it is a philosophical thing that it's got to be better for us in the long run to represent our world in terms of things that we can actually observe instead of things that we can never ever observe. So that's kind of the philosophical point that this answers. There is, as far as I'm aware, the literature that I'm familiar with in terms of learning a POM-DP, you can learn a PSR representation maybe easier than learning a POM-DP representation, but the thing that I find interesting is that there's POM-DPs that are easy to learn and there's POM-DPs that are hard to learn. And the POM-DPs that are easy to learn as PSRs, and the POM-DPs that are hard to learn as PSRs. So there's almost sort of this underlying toughness of the POM-DP itself, or of the environment itself, that switching to PSRs doesn't seem to exactly help. There is a case, though, when certain of the attributes of the problem are continuous, where, in fact, it can be shown that a PSR representation can actually be learned efficiently when the POM-DP representation is not clearly learnable efficiently.
I mean, I suppose one nice thing about the test model, like at least in a particular case where, there's like some 1 or 0 probability of a test coming out under certain circumstances, it might be easier to think about what you ought to do in order to figure out exactly where you are. Like the set of tests you might run so that you can completely determine where it is you are in the real sort of underlying world.
Just knowing that might be a useful thing. Yeah, for control and discovery.
Right.
Yeah, I mean, I'm not familiar with papers that do that exactly.
Yes, you are.
Do you have a paper that does that exactly?
Holmes and Isbell?
I guess I wouldn't think of it that way.
I always thought of it that way. Or at least Satinder told me that I should think about it that way. I didn't think about it that way till he told me I should.
And that, in particular, that's Satinder Singh, who his group did a lot of the pioneering work on PSRs and had some very nice analyses for how they worked. So yeah, okay, but I just wanted to give kind of a sense of this. There is some more recent work using least squares methods instead of probabilistic methods that actually can lean on this PSR idea to learn efficiently, actually. If you have enough data, it can actually turn it into a model that predicts well. And the model has elements in common with PSRs. So it has gotten some leverage. I think the jury's still out as to whether or not this is really the way we want to represent our environments, but it's a useful tool for the toolbox.
Yeah, I can see that.